Okay, so this is week 8, where we are going to see basically, yeah, week 8 basically material is mainly kind of a review of everything that was done before, right? Out of activation functions, losses, uh, back propagation, details of back propagation, things of that nature, right? And in keeping with that, we'll go through some problems, uh, go through some kind of objective type problems. And after the problems, I will show a hands-on example, like a Python notebook containing code that does neural network training as a simple training for a simple neural network from scratch, right? So you does the code explicitly does forward and backward passes, weight updates, right? So you can have like a full understanding of how such a thing works, right? And then conclude that, right? So let's start off. The first question. Uh, so here is a model, right? And it's a simple model. There's a X going into this one, uh, let's say, engine neuron. Rather, it's just one unit, right? So there is a weight with X, and then sigma activation function, and you get Y out of it, right? So the target is YL, stands for Y label, and the loss is mean squared error loss, right? So you have basically sigma of sigmoid function of Wx equals to Y, right? And you're trying to match this Y to YL. So the question here is basically which of these statements are true. First one is talking about the update rule, which you can verify based on uh, how we had talked about gradient descent, right? The second one is delta W depends only on the inputs of the network. Uh, then there were a couple of forms of this weight update, right? Gradient delta W, not specifically weight update, but rather the gradient of the loss with respect to W, right? So the question is which of these is correct. Right? So yeah, I will just wait for a minute or so, think about it, and then we'll discuss the solution. Okay, so here we can analyze this network, right? Which is it's a very, very simple network. You just have one input, one weight uh, activation function, right? So basically you have y equals to sigmoid of from w times x. That's the function. And first option obviously is true because this is a generic statement, and this will always be true for all networks that are trained by gradient descent. So weight update rule is w minus eta times grad and the gradient descent is the equation for gradient descent. Uh, Next is delta W depends only on the inputs of the network. This is not really true. It also depends on the label, right? And finally, uh, we have delta W equals y minus y. So here, so this is the equation that breaks down the gradient update. So we have this part, which is gradient with respect to W, right? So there is a gradient of loss with respect to W. So it's delta del L by del W, right? And this, the right hand side of it is the expression of chain rule, basically, right? So the first term is the gradient of the loss with respect to Y, which is the output, right? So we have, and since obviously output is given as mean squared error, so the gradient of that is nothing but Y minus YL, right? So gradient of del L by del Y. Then the next term you have is del Y by del wx, right? So we're multiplying x with w, and that goes into the activation function. So this, the middle term over here, is the gradient of the activation function, right? So if this is a, since this is a sigmoid activation function, gradient of sigmoid of x is nothing but sigmoid of x multiplied by 1 minus sigmoid of x. So we'll apply the same uh, formula here. We get the gradient of the sigmoid as sigmoid of wx times 1 minus sigmoid of wx. And finally, the last term here is you get x over here, which is nothing but the gradient of wx with respect to w, right? Remember that we are trying to compute the gradient of the loss with respect to the weight. So the final term is the gradient of this and the gradient of the pre-activation with respect to the weight, right? So this is how you basically uh, stitch together all of the partial derivatives, right? You get the gradient of the loss with respect to any weight, any or any parameter, right? It could be a weight, it could be a bias, it could be any other learnable parameter in the network. The way you get this gradient basically is by using chain rule. So you start at the final stage where exactly at the stage y, which is the output, right? Where your loss will actually be computed, and then you go backwards, right? So here, our like most final stage was at y. So we started here, got the gradient. We computed the gradient of the loss with respect to this y. Then we computed the gradient of this y with respect to whatever was input over here, right? So it's gradient of y with respect to wx. So that brings us here. And then finally we compute the gradient of uh, whatever was here, whatever went here with respect to the weight, right? So you go all the way backwards, and finally we get this expression, right? And this is kind of important. Uh, we will see. So I will show a hands-on kind of example notebook where I do compute the gradient computation, forward and backward pass gradient computations by hand, right? And there's a very good, very nice structure to this, which is that it's like a repetition of the same kind of behavior, right? So if your forward pass is defined, so for each type of layer, you will have the same type of gradient function that operates on the uh, backward trajectory, right? So you have defined the forward functions, and you have defined the backward functions of any given layer or any given operation, then you can stitch together as many layers as you want in your network, and basically it will work, right? Because you'll be kind of recurrently going backwards. Uh, yeah, going backwards until uh, reach whatever parameter you're trying to optimize, and then we do it for all of the parameters that are present in the network. Right? So, yeah, so this is brief revisiting of backdrop, right? Second thing, so here, so this is about regularization. Uh, this is specifically about two types of regularization. We have more broadly discussed L2 regularization in the earlier sessions, but here we're talking about L1 as well. L1 is nothing but you take the absolute value of all the weight parameters and you add them up, right? So that gives you your L1 one. And L2 you already know, you square all of the weight parameters and add them, right? So L1 is absolute value, L2 is squared value. So here we have L1 and L2, and the question is to basically match the type of regularization, uh, the type of uh, operational, the type of function that they perform, right? So yeah, I will give a couple of minutes for everyone to work it out, and you can answer in the comments in the chat. Then we'll discuss the solution. Uh, okay, answers. Anyways, that's okay. So we will anyways discuss the solution, right? So first of all, is you have to think about the shapes of L1 and L2 regularization, right? And exactly what happens when you do L1 or L2 regularization, right? So I described the functions. So for L2, for example, you have basically taking the squared values of all the weight parameters and adding them up, and that sum is added to the loss, right? And so when you are trying to minimize the loss, what happens is that simultaneously you're also trying to minimize the sum of the squared uh, values for L2 regularization and the sum of the absolute values for L1 regularization, right? And if you think about it, when you're trying to reduce the sum of the squared values, that just means that you are trying to minimize you're trying to minimize the, the absolute values in the sense uh, of the weight parameters, right? You are trying to shrink them towards zero. And so L2 regularization is very easy to understand. What it does is that it constrains most weights from taking large values, right? So if your weight has a smaller value, then your L2 regularization loss will be lower, and that will be like a good position for your network trading to kind of hit, right? On the other hand, there is L1 regularization, and just looking at it, you might think that it is doing a very similar thing, and in fact, it is doing a very similar thing. But because of the difference in uh, the nature or the functional form of the L1 and L2 regularization functions, what you have is that when you do L1 regularization, it doesn't just constrain the weights from taking large values. In fact, it tries to make them zero, right? And this will be easier to understand once we see these things, right? So this is your L1 loss function, right? So you have this on the x-axis are the weight values, uh, on the y-axis is the loss, and L1 is, like I said, nothing but absolute value. So you get this absolute value function, and if you take the gradient of this, what you will get is this, right? So if your weight value is negative, your gradient is -1. If your weight value is positive, your gradient is +1, right? And what this means is that uh, there is no real stable point on this L1 loss curve except when the value is exactly 0. So when the value is exactly 0, your gradient with respect to this loss becomes 0. So that's where your parameter values will try to go, right? So this is kind of the broad definition, broad understanding of how L1 regularization works. On the other hand, you have L2 regularization, where you have something like this, right? So you have this parabolic curve, just a squared value. And essentially what happens is that your gradient descent will try to bring the weight values closer and closer to zero, right? But the other thing that simultaneously is going to happen is that as your weight values become closer and closer to zero, the gradient that brings them towards zero will become smaller and smaller, right? So if your weight is somewhere here, right, it is feeling a very small gradient towards zero compared to if your weight was over here, right? So if your weight was over here, there's a strong kind of push, or rather pull towards zero, whereas if it was somewhere over here, it is a very mild kind of push over here, right? So, and the same thing is true on the other side as well, right? So the further it is away from zero, the stronger is the kind of attraction towards zero, and then as it gets closer, it becomes less and less strong strong, and basically what will happen is that your weights will kind of settle down in this range, right? So somewhere around zero, but not exactly uh, that way, right? So this is how this thing works, broadly speaking. And this is, but of course, this is all theoretical. This you can use, I mean, you can use L2 regularization and then you can prune the smaller values to get a sparse network, right? Uh, so you can work on something, right? So if you want sparsity, you can even kind of enforce sparsity from L2 regularization. Okay. Yeah, okay, I'll speak closer to the speaker. Okay, so it's regularization. Next part here is pre-training. So this is old kind of pre-training from before certain techniques were developed that allowed people to train neural networks. So back in the day, uh, it was it was very difficult to train deep neural networks. In fact, there was this very common problem of gradient gradient vanishing or gradient explosion that used to happen uh, depending on the length or the depth of the network. And people developed innovative ways to kind of try to deal with that. And one of the ways that people develop, in fact, this is the ways that was developed by Jeffrey Hinton, is this thing called unsupervised pre-training, right? Which is kind of based on the idea of like autoencoders, right? And basically, the idea is that if you have for every layer, what you do is that you do first do a pre-training where that layer kind of learns the relationship of performing an autoencoder function, right? So given an input to that layer, it has to be able to uh, perfectly reconstruct the input. So you do this autoencoder based pre-training, and then you train the entire network based by using gradient descent or whatever, right? Backpropagation. So yeah, so this question is about unsupervised pre-training. Obviously, for this kind of pre-training, you don't need supervision because you're doing an autoencoder function. So which of these statements are true, right? Unsupervised pre-training initializes random weights. Pre-trained weights are finely tuned by supervised objective function, right? And based on the discussion that we talked about just now, this should be fairly simple to answer. Uh, okay, so basically here, so this is based on the discussion that just had before. Obviously, both of these statements, the second statement is true, right? First statement is obviously not true because we talked about unsupervised retraining, where you are trying to make every layer perform an autoencoder task, right? Which is obviously not initializing random weights, right? So you don't initialize random weights. Instead, you initialize weight such that it is capable of doing autoencoder, capable of doing an autoencoder task, right? So that is the initialization. And then the pre-trained weights are fine-tuned by supervised objective function, which is standard, right? So here is an example, basically. So you have multiple hidden layers. So this is your input, let's say. This is your first hidden layer. Unsupervised pre-training basically makes it so that this H1 is able to perform a autoencoder function on this X, right? So H1 is able to reconstruct X with the same weights, right? So you also apply this concept of weight tying, where basically the same weights are used for the encoder as well as the decoder, right? So yeah, so this is unsupervised pre-training. Uh, Fortunately, we don't really need to do this anymore, right? So eventually what happened is that people figured out these. So the first kind of activation functions that people were using were like the sigmoid activation functions or tanh activation functions and so on. And all of these activation functions had this saturation problem, right? So sigmoid, when it goes high, it gets saturated, and tanh is also the same. When it goes high or low, they get saturated, which means that the gradient becomes very small, right? If the function, if the activation function becomes saturated, then the gradient obviously will become very small. And then what happens is that as you uh, do backpropagation across the layers, it becomes smaller and smaller, right? It becomes exponentially small, and all of your earlier layers, they don't learn anything at all, right? So that was the problem, and that is the problem. It's called gradient vanishing problem, and things like this helped to solve that problem somewhat. Uh, Eventually, what happened is that people figured out better, both better initialization schemes, right? So this random initialization that you perform on for the weight matrices, for that, so specialized schemes were introduced based on statistical analysis, right? So based on the number of neurons in the previous layer and the number of neurons in the next layer, you set up some sigma values, right? We have a zero mean and some sigma values, and then based on the distribution, right? He takes values out of a uniform distribution or a normal distribution based on using the mu and sigma values that you have computed, and that gives you a good kind of starting point, right? So this was one of the things that uh, so this was one of the ways that people figured out to make deeper networks work. And then the other thing that was developed was like simpler activation functions like ReLU activation function, right, which did not have this saturation problem. So ReLU activation function also helped to improve uh, implementing deeper networks. And then other things were developed that made even more deeper networks possible, right? So there was ResNet, which is short for residual networks. So that was developed later, uh, and so on and so forth, right? So before ResNet, based on this initialization in ReLU, you could do something like 10, 20 layers, around 20 layers. And then after ResNets were developed, it became possible to do like 100 plus layers, like 150 layers or something, even more than that. So that's like the chronology of methods that have been developed to tackle the problems that arise with having deeper and deeper networks. Right? So yeah, so we'll move on. So this question is about the importance of having activation functions, right? So here you have a network, let's say. Right? So you have one transformation from X to H1. You have this weight W1, and you have sigma. Then you have W2, you get H2. You have another sigma, and then you have another W3 that gives you Y finally with the third. So the activation function is exactly the same. It is just the sigma function. It could be anything, right? You can assume that it is like a sigmoid function or something. But uh, but yeah, so here, so you assume that they were originally sigmoid functions, and then we replace all of the sigmoid functions with linear functions, right? So this sigma kind of circle that you see here, sigma block. So this has been replaced with a linear function, which is just passes out whatever input was received to, right? So we no longer have non-linear activation functions in this network. And then the question is which of these following statements are true, right? So yeah, think about it for a couple of minutes. We will discuss the solution. Okay. Uh, so basically for this problem, uh, what we are doing essentially is we are replacing the non-linear activation functions with a linear activation function, right? And what that is going to do is basically it will make this system such that it can only perform linear decision boundaries, right? So model can only learn linear decision boundaries because this model kind of compresses. There's basically this model with three sets of parameters, right? So there is W1, W2, W3. Without the nonlinear activation functions in between, this model will essentially collapse to a single parameter, right? So basically, what you do is we just write this function, right? Now that we don't have the activation functions in between, essentially what you'll get is this, right? So basically y equals to w3 times w2 times w1 times x, right? So these w1, w2, w3, they are basically matrices, right? Weight matrices. So we are doing a matrix multiplication, but matrix multiplication is associative, rather it's, it's associative and it's distributive, right? Which means that you can get rid of these brackets in between and multiply these matrices, right? So you can w3 times w2 times w1, convert that into a giant into a single matrix, which I'm calling capital W, right? So you can compress that into this capital W, and then basically you have this y equals to capital W times x, right? Which is a single parameter network, single layered network, right? And obviously a single layered network can learn linear decision points, right? So this problem emphasizes the importance of having nonlinear activation functions, right? Because without the sigmoid functions in between, uh, all of these, so many parameters basically go to waste. So these W1 parameters, W2 parameters, and W3 parameters, they all get compressed down to a single weight matrix, capital W, right? And that's a waste, right? Because this is going to have fewer parameters than whatever is the total number of parameters you had, and it's going to be less efficient in terms of memory, and it's also going to be less powerful because it's a simple uh, yeah, right? So this is this kind of demonstrates the importance of having linear activation functions. So in that sense, really fun. So here, this is the one activation function I spoke about briefly. It's called the ReLU activation function, which is short for restricted linear unit. Right? And if you know the ReLU activation function, this question is very simple. Right? So in the ReLU activation function itself is a classical function, right? So yeah, there's nothing more to say about it. I'll just give some time for you to work out the right answer, and then we'll discuss. Okay, so uh, ReLU functions, just bring out the definition and everything else will become clear. So ReLU function is simply defined as max of x comma 0, right? Value of x is equal to max of x comma 0. Basically, if this x is less than 0, you get 0, and if it is greater than equal to 0, you get x, whatever is the input, right? So what this means is that the gradient of this function is also very simple. Gradient is 0 if x is less than or equal to 0, and it is 1 for x is greater than 0. You might note that this is, strictly speaking, not a differentiable function at x equals to 0. So the gradient is separately defined to be 0 for this one, right? So yeah, obviously it's very inexpensive, right? So you just do one comparison against 0, you get your output. Then obviously it does not saturate because it keeps on rising. It's linear in the positive region, right? And the third thing is that it converges faster than sigmoid, uh, which is related to the same kind of problems, right? It does not have the gradient vanishing problem, so it's more effective in learning in like deep networks, right? What it is not, however, is zero-centered, right? Obviously, this is not a zero-centered function, right? Because there are no negative values that it can take. Yeah, so it's fairly very useful. And for a while, this was the most dominant. And in fact, it is still very, very dominant, right? What has happened recently is that people have developed certain variants of ReLUs, which are slightly more computationally intensive, especially for the negative side. But at the same time, it has these attractive characteristics of non-saturation, things like that, right? So yeah, so that was ReLU. Now we will do kind of the inverse problem, right? So I'm giving like set of characteristics, and the question is to identify uh, the activation field, right? So the characteristics given here are: one, it compresses output values to -1, 1. Then two is that it does zero-centered outputs, which is kind of a expected given number one, right? So if your outputs are compressed to -1, 1, it's likely to be zero-centered, because typically such kind of functions will be also symmetric, right? Asymmetric and bounded uh, negative and positive, then you should get zero-centered. And finally, third is gradient vanishes, right? So there is a saturation problem that happens with this function, right? And given the options, you should be able to kind of figure it out. Okay, so given these characteristics, it's kind of pretty obvious what the answer will be. In fact, it is 10H, right? So we know just such a book obviously well, it does not fit into these uh, properties, right? Linear also does not fit, obviously, because linear for one doesn't compress the outputs to anything. And then you have, so that then you're left with sigmoid and 10H. Sigmoid is not zero centered, and in fact, it saturates from 0 to 1, right? It compresses to the range 0 to 1. So it just leaves 10H, which satisfies all of these properties, right? So if you draw the plot of 10H, for example, it looks something like this. On the negative side, it saturates to -1. Positive side, it saturates to +1, right? So here, so this one is talking about the issue with value neurons and having biases, right? So if you assume that there is a large negative bias to a certain neuron, and because of that large negative bias, the ReLU neuron has died, right? It is not giving any output. Because remember that if the input to the ReLU neuron is negative, you will get 0, right? So if the input becomes if the input becomes like always negative because there is a huge negative bias attached to that neuron, then that neuron will kind of die in a sense. That's what is being described here. The question is that what happens to the future state of this, right? Does it stay dead or is it able to recover? Uh, okay, so basically what is going to happen in this case is that the neuron will become permanently dead, right? So you have described what happens up until this point. Basically, you have a large negative bias, and that large negative bias is forcing the ReLU neuron to give 0 output for almost any input, right? What will happen then as a result of that is that the the gradient will no longer pass through that neuron, right? So if the output of the value is 0, then the gradient is also 0, right? Yes. If the output is if the input is if the output is 0, then the gradient is also 0. And if the gradient is 0, then yeah, if the gradient is 0, then you know it's no longer going to give any signals back that that can update the weights that are feeding into this neuron, right? So those weights will never change, and if the weights never change, then there is no way for this particular neuron to overcome this negative bias that is appearing, right? If the large negative bias switches off a ReLU neuron, it will stop updating its weights and it will even further updating, right? And this is a problem for neural networks with radio activation functions. And the way you typically deal with it is by simply not having biases at all. Right? So you just get rid of the bias, train neural network with weights only, and activation functions are ReLU. And because this ReLU has There's this kind of a threshold, right? But if uh, if the input value is less than zero, you get output as zero, right? So that thresholding function of the ReLU kind of behaves like bias itself, right? So you don't need an additional bias for them. So yeah, so that was the problem with the ReLU and having like biases. And basically, like I said, we saw deal with that is get rid of the biases, right? So you train networks without biases, right? So this one is, I believe, yeah. So this is a final question for this week's material. So here are three plots, right? So these are ReLU, uh, leaky ReLU, so-called leaky ReLU, and exponential linear unit, right? ReLU and its kind of derivative, you know, variants of ReLU, right? So the question here simply is match them. Right? Which one is ReLU? Which one is leaky ReLU? Which one is exponential linear? And that's it. Will be done, and then I can briefly show you the code notebook, right? That talks about that describes the whole process of neural network kind of forward and backward passes, such. Uh, okay. So yeah, basically, if you look at the shapes, you think about the function, and if you think about the names, it should pretty fairly straightforward match them, right, with the plots. Obviously, B is the original ReLU, right? Restricted linear units. You can see that it's zero for negative values and then takes the linear format, right? Exponential linear unit is obviously option A, right? You have a exponential looking curve in the negative uh, axis, which is in fact this is nothing but uh, e to the power of x minus 1, right? So we do e to the power of x minus 1, you get this curve, and then on the positive side, you extend it in a linear fashion, right? So in the positive side, you just have y equals to x. So this is exponential linear unit, and then this final thing over here, option C, is nothing but leaky, right? So the leaky part comes from the fact that Negative side is not exactly zero, but rather it has a very small negatives, very small positive slope, right? So on the positive side, the slope is one, uh, similar to a normal gradient, and on the negative side, the slope is some very small value. But this is often sometimes this negative slope itself can also be treated as a parameter of the model, in which case it is called as parameterized leaky rate. Right. So it is three variants of values, and now I'm gonna go and look into this. Right. So basically, this notebook which I shared. So this notebook contains code for both forward and backward passes. Right. So you have neural network training situation and system. So basically have forward pass and backward pass, right? You do the forward pass to generate the outputs, and then you do the backward pass to update the weights, right? So you do backpropagation in the backward pass and then you update the weights uh, using gradient descent. And normally what you do is when you write a network using these deep learning frameworks like TensorFlow and PyTorch, you just take care of the forward pass, right? And if all of the functions that you are using in the forward pass are functions of that particular framework, then the backward pass is automatically handled, right? So is something called as an uh, autograd implementation, right? Which just stands for automatic gradient descent or automatic gradient, right? So if we define a function, then uh, if you define a function that is composed of like known functions, functions that are known to the framework or part of the framework, then the framework itself will automatically define the backward pass flow of information, backward pass functions, transformations, whatever it is there, right? So here in this notebook, what I'm trying to do is I'm trying to expose this uh, automatic function that generally happens under the hood, right? Because it is good to know uh, how how exactly the how exactly the neural network is able to update its weights, right? So we'll do like a basic neural network implementation thing. Uh, simple using a simple yeah. So we'll do like a very basic neural network implementation using very simple uh, data set, right? And a simple network, which is just like a two-layer network is what we will do. And then I have a list of activities. I will obviously, the notebook is obviously shared, right? So you can get it. Uh, so part of this here. So yeah, so here is the notebook, and there are suggested exercises uh, in the PPT that you can try, right? So let's go to the notebook. See. So yeah, so we have a startup, right? So here I'm going to use using TensorFlow. Until now, I have explicitly used TensorFlow only, but we will see some examples of notebooks with PyTorch as well in the coming weeks. Uh, so we have TensorFlow, and these are kind of importing, getting rotating the uh, libraries, right? So we have NumPy, this is sklearn, scikit-learn. Um, important thing is this, right? So we'll get the data set from this sklearn data sets. It's nothing new. It's a data set that we have already seen. It's just MNIST and its variants, right? So we have MNIST and fashion MNIST. Right. So how MNIST and fashion MNIST, this one is fashion MNIST is also, they are very similar. They are 28 by 28 images that are single color, like black and white images. And MNIST had digits, right? So digits of 0 to 9. And fashion MNIST has like miniature images of clothing items, right? That's why it's called fashion MNIST. So yeah, so we'll load the dataset first. Right? So we are getting it from this OpenML sklearn datasets. And yeah, so there is a normalization that is happening, right? So you apply this normalization. This is basically scaling values from scaling values to 0 to 1 range, right? So you're subtracting the minimum value and then you're dividing by max minus min, right? Which will normalize to that 0 to 1 range. Then we do a random permutation so that it permute the jumble up all of the samples, right? And you split the data into training data. So X data and Y data is your training data. X test and Y test is your test data, right? And here you do something that is kind of important. Is what we get one hot encoded one hot encoded labels, right? By default, labels just have the label ID, right? But if you actually want to do this training by hand, right? If you actually want to write all of the functions, what you have to do is perform this one hot encoding, right? And one hot encoding is nothing, it's very simple. Basically, what you are doing is that uh, whatever was whatever was the label, right? So for that label, you set the value to be 1 and everything else is 0, right? So the correct level has a value of 1 and all of the incorrect levels has a value of 0 for any given sample, right? So this is, yeah, so this loops through all of the samples, and you set the labels, right? So we do one hot encoding of the labels. And here, so these functions basically define, so these are your layer functions, right? And we have basically two types of functions. The first function is so this is FC, stands for fully connected layer. So FC, it takes input as X and W. Right? W is the weight, X is the input. And basically it just returns TF and ReLU. So I apply the ReLU activation function, and what you apply the ReLU activation function is basically you apply it on matrix multiplication of X comma W. You do TF dot multiple X comma W and then you apply ReLU and you return that. For the output layer, it is slightly different because for the output layer we want softmax. Right? So output layer does TFM softmax. So here, in fact, instead of having it like this, you could even simplify it by adding an extra parameter that says what kind of activation functions you want, right? So for the output layer, you pass softmax. For any other layer, you pass trend, right? And then you have the backward pass functions. Okay. So backward pass function is also similarly divided into two types. And here is, I mean, here you can't really uh, combine and club them together because the backward pass of the gradient calculation at the output layer is fundamentally different from the gradient calculation at any other layer, right? So at the output layer, you have a gradient calculation that looks like this. It's a grad equals to minus of y minus level, right? And if you remember our discussion about softmax cross entropy, softmax plus cross entropy loss, you will realize that what I'm trying to optimize for here will eventually be softmax cross entropy loss, right? So this is the gradient of softmax cross entropy loss, and then you have the vapor pass for the fully connected layer, where it takes x, which is the input side, the gradient post, it is the gradient coming from the next layer, right? So the gradient coming in the backward direction from the next layer, and this is the weight that is connecting the gradient coming from the backward direction from the next layer to this current layer, right? So you apply grad equals, so you have matrix multiplication, right? So this is how the gradient flows in the backward direction, and so you have gradient post multiplied by transpose of the weight, right? And then you multiply this with this, right? So this part, the second part here, which where I'm just taking x greater than 0 and I cast it to floating point. So this part is nothing but the gradient of the Rayleigh equation function, right? So this second part is the gradient of the Rayleigh activation function. This first part is the flow of the gradient from the next layer to the previous layer, right? And then you combine them two and both of them and you get the gradient. Right? And finally, weight updates. So weight updates is single function, right? So you apply, and basically what you need for the weight updates are three things: the post gradient, which is the next layer uh, next layer gradient, the x pre, which is the previous layer activations, and eta, which is the lead, right? And the dw gradient update is nothing but eta times df matrix multiplication transposed uh, pre-layer activations multiplied with post-layer gradients, right? So you have df dot transpose x pre and grad post into matrix multiplication of them and multiply by the learning rate addition, right? So eta times this. So this will give you a dw, right? An important thing to note here is that this negative sign that we do for gradient descent, we have to do a negative of the gradient movement, right? So that negative sign is already taken care of over here, right? So we have this minus of y minus level that takes care of that negative sign. So we no longer have to think about negative. So here is a definition of a single layer, single hidden layer. It's a definition of a single hidden layer neural network, right? There's a two-layer neural network, single hidden layer. And this is what is called, so this one right here is uh, initialization, weight initialization, right? Weight initialization. So this is what I was talking about, that you perform statistical analysis, and there was a statistical analysis that was performed, and you arrived at, and people arrived at certain rules. So this is called key initialization based on named after authors of the paper, right? Initialization or severe initialization, right? So yeah, so basically what you do is what people found out is that if you take the if you take like the standard deviation and you equate that, if you take like 1 by n, square root of 1 by n, right, where n is like the number of inputs coming into the layer, right? If you take square root of 1 by n and use that uh, as the standard deviation of the random weights that you're going to sample, then this is a good initialization scheme, right? So this is, I mean, there is a statistical analysis. Obviously, I'm not going into the details of that. You can read up the paper, it's very interesting. So yeah, so basically, so with this we have now initialized the weights, and then yeah, so we convert these weights. So these were NumPy arrays. We convert them to TensorFlow tensors using this TF constant, and then we train this network for 5 minutes. Right? We have set the learning rate to be 0.001, and yeah. So for the training loop, it's nothing too complex. You just divide. Number of batches is just data size by batch size. Number of test batches is data size test by batch size. Uh, Here I have not set a dropout probability, but you can set it dropout probability, right? And if you set it, not used it actually. So, yeah, so if you set dropout, you may have to use it. Basically, what you have to do is modify this mask gauge, right? So, but yeah, I mean I'll just leave that as an example. Try to do it, right? So go through the dropout paper, see how it is implemented, and then you try to implement this by hand, uh, like by your based on your own understanding, right? And then you see that whether it works or not. So yeah, so dropout. Let's ignore that one. Then we have yeah, so we get the batch. So this is the batch X where take its data and take like the batch size amount of out of its data and then convert it into TF dot tensor, tensor per tensor. So then first we do one layer. So this is first layer neural network, right? And then this is the second layer. So you get FC out. So this is your output. This is your forward pass, right? So layer one, layer two, and then the backward pass. I can actually this, this. Yeah. So yeah, forget about this, right? So this is something you will need if you're going to use, if you're going to actually do the dropout thing, right? So this is a forward pass, backward pass also very simple, right? First thing is you get the batch level. Let's put this together. This is here, right? So you get the batch X and you get the batch level, and you do the forward pass. So it's just two layers. Then you do the backward pass, which is also similar, just two layers, right? So the last layer, so forward pass obviously goes in one direction and backward pass goes in the other direction, right? Forward pass you get first layer, then second layer. In the backward pass you get first the backward pass of the output layer, right? So you get BPFC out first, and then you get BPFC backward pass of FC layer, right? So backward pass of FC out. For that you need this Y, and you need the batch label. So this will generate gradient with respect to Y, and then you send it back further, get gradient with respect to H1, which is the hidden layer, right? Through APFC. And finally, you do the weight update calculation, which again is just two steps because there are two sets of weights, right? So there is a W1 and there is a W2. So you get W2, you do get TW. So W2 will basically get for W2 the post layer gradient is GY, and the pre-layer activation is this H1B, and training learning rate is obviously data. For W1, the post layer gradient is H1, and the pre-layer activation is batch X, and that is obviously the same, right? So you get DW1 and DW2, and finally you just have to do W2 is equal to W plus DW1 and W1 equal to W plus DW, right? So you can update the roles. So this is the functionality. So you have forward pass, backward pass, weight update, calculation, and then weight update application, right? And then, yeah, so this is in its later part over here is nothing but just like computation uh, of the accuracies, right? So here we are computing accuracies inside the training, and then later separately we'll compute the accuracy inside the test. Obviously, for test, you only need forward pass, right? So you have one part over here. Yeah, so for this, you just have that, and then you just print the values, right? So let's do this again. Set things up over here. Let's train it again. Train it for 10 bucks. Afterwards, months, right? So yeah, I mean it's training. This is this is this is fashion MNIST. You can do MNIST also. Yeah. So this is kind of a simple thing, right? And then the important thing is that yeah, you can basically play around with this, right? And you can try to implement these concepts from neural network papers, and you can try to see if your own understanding is good enough, right? That this is what you understand of the method. And try to implement it, and then you see whether your understanding matches with what is expected, what is described as in the paper, so on, right? So yeah, so let's go here finally. Ah, forward and backward pass. So here the notebook is shared, and some suggested exercises, some exercises are suggested here. You can try this out, right? You can try training a deeper network, which is very simple addition if you want to do it, right? Just have more of those function calls. You have to define more rate parameters, and then you have more of those function calls. Then the second part is implementing regularization, which again is kind of simple, right? L1 and L2, uh, L1 and L2 are fairly simple functions, right? And then based on the L1 and L2, what you have to do is not just understand what is L1 and L2, you have to understand what is the gradient of L1 and L2, right? And then that gradient will be added up to the weight update side of things, right? So you add that L1 gradient and L2 gradient, the weight update side of uh, your calculations, right? And that will take care of implementing regularization. Then the third thing is you change the activation function, right? So here I'm using ReLU activation function. Obviously, for the output layer, you will not change it, right? So you can swap this ReLU with something else, right? So you can swap this ReLU with something else, and then what you'll also have to do is that if you swap this ReLU with something else, you have to change this PPFC function as well, right? You have to change this part of it. So here, so this is the gradient of the ReLU, but if you do sigmoid, for example, then you have to apply the gradient of the sigmoid over here, right? So yeah, so that would be changing the activation function. And then the fourth thing that you can do is you can implement an advanced optimizer, right? So here the optimizer is nothing but simple batch gradient descent, mini batch gradient descent, right? You see that I'm just multiplying eta with whatever I'm getting, right? Gradient goes multiplied by x3 and then multiplied by eta, right? So this is simple batch and mini batch gradient descent, right? You can enhance this with like momentum, we can enhance this with the Nestor of, can enhance this with Adam optimizer if you like, right? So basically test your understanding of those methods, right? So yeah, I mean, it's a very basic setup, right? But all of the building blocks are there, and basically you can try to implement some of these advancements of neural networks learning by yourself and test your own understanding of the ideas presented, right? So we are done. I think I'm done with I'm done with the material for this session. Have a, if you have doubts or questions, you can ask. Otherwise, you're free to leave the call. Uh, okay, there doesn't seem to be any further questions, in which case I'll end the call. Thank you for attending.